Hey folks, how y'all doing? This is section 3.3. We'll go ahead and get started in a second. Just a little bit of a heads up. This is a short section in the book, but it sets up the pieces for the next section, which is a long section. So, in terms of budgeting your time, just a heads up that the next video after this one was going to be a little bit long. All right, let's get started. So we'll start with the definition. We have a set of vectors. We say that it is a basis for Rn if it is both a spanning set of Rn and it's linearly independent. So we've seen this idea before when we talked about invertibility. In order to span Rn, that means there must be a row in every column. I'm sorry, a row in every column. That doesn't make any sense. How about a pivot position in every row? Excuse me. I'm sorry about that. But to be linearly independent, there has to be a pivot position in every column. And so, in order to be a basis for Rn, both of these things have to be true, which means that if we form a matrix out of these, the matrix that has V1 through Vm as its columns is an invertible matrix. So all of these things are true. But a basis is a spanning set that is also linearly independent. So as an example, which of these sets is a basis for Rn? So if we look at number one, if we could put this in echelon form in one step by taking row 2 minus 2 times row 1. So 2 minus 2 is 0. And 4 minus 1 is 3. And we have a leading entry in both rows and both columns. And so, yes, this is a basis for R2. So B is a basis for R2. So let's look at this one here. 1, 1, 1 in the first column, 0, 1, negative 1 in the second column, 1, 0, negative 1 in the third column. So let's try a couple things. Row 2 minus row 1 and row 3 minus row 1. 1, 0, 1, 0, 1, negative 1, because we're subtracting the row above it, and 0, negative 1, negative 1 minus 1 is negative 2. And then we can get rid of this entry by taking row 3 plus row 2, and that leaves us with 1, 0, 1, 0, 1, negative 1, 0, 0, negative 3, and we have 3 leading entries in 3 rows in 3 columns, and so this B is a basis for R3. Okay, let's do 2 more. All right, already I know that there's going to be a problem with number 3, because if I have 4 vectors, they cannot be linearly independent. I cannot have a leading entry in every column. Too many vectors. Cannot have a leading entry in every column. And so this is not a basis. All right. Number 4, I'm not even going to write the matrix. If you look at this, you can tell that it is already in echelon form. And in fact, this is not just a basis. This is E1, E2, E3. This is what we call the standard basis, is the standard basis for R3. So yes, it's a basis, but that specific basis has a name. It's called the standard basis. All right, let's move on. We have a theorem. Set of base vectors forms a basis for Rn if and only if this matrix is equivalent to an identity matrix. That, in other words, that because the columns of A are a spanning set and a linearly independent set, there must be a pivot in every row and every column, which means that the echelon form just looks like an identity matrix. And that means that any basis must form a square matrix. If it's not square, we can't have a leading entry in every row and in every column. All right. Every basis defines a coordinate system that we can use in place of the standard coordinate system for Rn. In calculus class, you dealt with polar coordinates as an alternative to the standard coordinate system. And it's found, some uses and some problems that could be done in polar coordinates. Every basis defines a coordinate system that we can use to replace the standard coordinate system. And so what we're going to do here is do some work with some of these alternate coordinate systems. So here's an example. We have these two vectors. These vectors are linearly independent. We did this row reduction already in example 1. And so we have a vector whose coordinates in the B coordinate system, that is using B as the coordinates, that vector has coordinates 2, -3. And this is what that means. And this is how we write this. But let's go ahead and sketch this out. This is my standard axes, but these are my new basis vectors. So our first vector, B1, is 2, 1. And my second vector, B2, is 1, 2. When we write 2, 3, but this little subscript here says that we're using B as our basis, this doesn't mean 2 in the x direction and -3 in the y direction. It means 2 in the B1 direction and -3 in the B2 direction. And so this is going to be the linear combination. 2 times B1. That's 2 times B1. And then we're going to add to that -3. So we're going to go back in the other direction. So 1, 2, 3. That's -3 times B2. And this is the point whose coordinates are 2, -3, but in the alternate coordinate system, where I'm using B as my basis instead of my standard basis. So the problem says to first sketch V. Well, we just did that right here. And now let's find standard coordinates. What is the standard way we would refer to this point? Well, the standard way would be we would figure out what 2 copies of 2, 1 are, minus 3 copies of 1, 2. What is that linear combination when we weight this? And in the top row, we get 4 minus 3 is 1. In the bottom row, we get 2 minus 6 is negative 4. And so the standard way of finding this point is to go 1 unit in the x direction and 4 units down in the y direction. So this is, 1 in the x direction and 4 in the y direction. And I know that green is a little hard to see. I'll get back to red and blue. All right. So the standard coordinates are 1 and negative 4. So we've just given a point in an alternate coordinate system, and we converted it back into standard coordinate system. All right. Let's try a harder example. Here's my basis now. So my basis is now, my B1 vector is 3, negative 2. And my B2 vector is 2, positive 1. So that's my B2 vector. And I'm looking at the point in alternate coordinates. In alternate coordinates, the point is negative 2, 4. So how do we find that? We first go negative 2 units in the B1 direction. So that's negative 2 copies of B1. And I'm going to go up in my header here. And then 4 units in the B2 direction. So that's going to be 1, 2. I'm going to go off the top of the screen. That's okay. But somewhere up there is the linear combination that we're looking for. That's negative 2 copies of the first vector, B1, and 4 copies of the second vector, B2. So in standard coordinates, we would go 2 units in the x direction and 4 units in the y direction. When we see this notation here, it means instead of using x and y as our reference directions, we're using these vectors as our reference directions. Well, we can solve this. This is negative 6 plus 8 is 2, and positive 4 plus positive 4 is 8. So that's 2 units over and 8 units up, which again takes us a little bit off the top of the screen. The second question, though, is a little trickier. If we want to look at the point 3, 5, and there's no B here. This is standard 3, 5. And so this is to point 3, 5. The question is, how do we find that point using B coordinates? How do we describe the location of that point in terms of B? Well, then we need to figure out a combination of these 2 vectors that adds up to 3, 5. But if they add up to 3, 5, that sounds like a system of equations. That is, we're going to take 3, 2, 2, 1, augment this with 3, 5, and we're going to try to solve this. All right. Well, first thing we have to do is get rid of that negative 2. So we're going to use a 6 to cancel. This is going to be 3 times row 2 plus 2 times row 1. So let's see. 6 and -6 and +6 are 0. 3 and 4 is 7. And 15 and 6 is 21. All right. So this tells us that 3x plus 2y is equal to 3 and 7y is equal to 21. So I know that y is equal to 3, and therefore 3x plus 6 is equal to 3. And so 3x is -3, and so x is -1. And so in the alternate coordinate system, this point should be -1, +3. In other words, if we go -1 unit in the b direction, so that's going to be right here, 1 unit the opposite of the b direction, and then 3 copies of b2. So that's going to take us 1, 2, and 3 copies of b2, and that does lead us to the point 3, 5. Okay? And we could check that just by making sure that -1 times the first vector and +3 times the second vector actually does add up to 3, 5. And that works. -3 plus 6 is 3. +2 plus 3 is 5. And so that checks. All right, let's move on. So let B be a basis for Rn. How do we go about converting from alternate coordinates to standard coordinates? And how do we convert from standard coordinates to alternate coordinates? Let me open this up here. So let's talk about how to do this. We just did this in the previous slide, so let's go back to here. When we started with alternate coordinates and we had to find the standard coordinates, we multiplied out a linear combination. We applied the alternate coordinates as weights in a linear combination and then just multiplied out the linear combination. Use the alternate coordinates as weights in a linear combination using the vectors in B. So alternate standard is just solving out a linear combination. The other direction is a little bit harder. Let's go back and look at that one for a second. To convert from the standard coordinates to the alternate coordinates, we need to take the vectors in B and augment with the standard coordinates and then row reduce to solve for the coordinates that we wanted to use in the alternate coordinate system. So it's not just working out a linear combination, it's finding the weights for a linear combination, which requires row reduction. We don't know what the weights are to begin with. So let's say form an augmented matrix with the vectors in B on the left and the standard coordinates on the right. And then solve for the alternate coordinates. And so we have a procedure to convert in both directions. We just have to keep it clear in our head which direction we're going. All right, let's go ahead and move on. So as a definition, a subspace of Rn is any subset that is the span of a set of vectors. So this is just kind of, same word almost. All spans are subspaces. We're just introducing a new term for the idea. So a subspace is a span. So why is this set a subspace of R3? Well, because it's a span. That is, when we put the word span in front of this says, so first of all spans are subspaces. But the word span says something. It says we are not just looking at these 2 points, but the span contains all of the linear combinations. So let's sketch this out and see what we're looking at here. We're in 3 dimensions. This is the vector E1, which is 1 unit in the x direction. And this is the vector E3, which is 1 unit in the z direction. And if I take a linear combination of these, for example, 2 times E1 plus 4 times E3, well, that's just a vector 2, 0, 4. That's 2 units in the x direction and 4 units up in the z direction. That's that vector there. Let's see, 3E1 plus E3 is the vectors 3, 0, 1. We can go 3 units in the E1 direction and 1 unit up in the E3 direction. And that's that vector there. E1 minus E3 goes 1 unit in the E direction and 1 unit in the E1 direction and 1 unit down in the negative E3 direction. And that's that vector there. All of the linear combinations we get, no matter what weights we plug in, are going to be some combination of an x coordinate and a z coordinate, and they're going to live inside the xz plane. And so the question is to describe this subspace. The description is that the subspace is the xz plane. All right. Okay. Okay, so let's move on. I have this set here of vectors of the form 4s minus 3t, 2s plus t, negative 3s plus 3t and t, where s and t could be any real numbers. Why is this a subspace? Well, I can rewrite S in this form. S is the set of vectors of the form S times 4, 2, negative 3, and 0, plus T times negative 3, 1, positive 3, 1. And these are linear combinations. And since S and T could be any real number, in fact, we get all linear combinations this way. And by definition, the set of all linear combinations is a span. But the set of linear combinations is a span. And so this is the span of the vectors 4, 2, negative 3, 0, and negative 3, 1, 3, 1. And all spans are subspaces. So since all spans are subspaces, then S is a span. It's just not written in the form of a span. S is a subspace. Because the second part of the question says to describe the subspace. Well, I can't draw four-dimensional space. I can't draw an x-axis and a y-axis and a z-axis and then whatever comes before z. I just can't draw that. So, some system where we have four axes, x and y and z and w. But you can imagine that such a system exists and that these are two vectors that are in that system. So this was the first vector, and over here is the second vector. And the linear combinations of those two vectors, just like in the last example when we did combinations of x and z, combinations of v1 and v2 are going to lie in the plane containing v2 and 1 and v2. And so this subspace is a plane containing v1 and v2. I can't draw it, but I can at least describe it. All right, that's it for this set of slides. What we're looking at next time, we've set up the definition of a subspace. A subspace is a span, and we're going to talk in specific about three subspaces next time called the column space, the row space, and the null space of a matrix. And we'll do some examples of those. And because we have three different types of subspaces to look into, it's going to be a little bit longer than usual next time. Just bear with me. Take care. I'll see y'all around.